Everyone. Let me start by thanking Neil first of all for making this event happen and inviting me. So thanks to her. Like she said, my name is Rohit. I'm a PhD student, and the stuff I'm going to talk about today is, besides being interesting, is also part of my thesis. So I'm even more excited to talk about it. Uh, so the topic for this mini lecture series is going to be fair division. Uh, and before we get into the mathematical nitty-gritties of it, just want to get a sense of what people think of when they hear the words fair division. Uh, what kind of things would you, in your daily lives, like to divide fairly? Uh, whatever. Any ideas? Such as? Yeah, you have a birthday cake and you have a bunch of kids who all want to grab the entire cake, but it won't be fair. So you want to divide it so that every kid is happy in some sense. So yeah, literally you can divide a cake. So cake is something that you could divide. Uh, what else? What kind of other things could be divided? Sorry, could restaurant bill? Yes, exactly. Yes. Uh, so you go out with a bunch of friends, and well, someone has to pay the restaurant bill, right? So the difference with cake is that you want more and more of cake, and with restaurant bill you want to pay as little as possible, unless you have great friends. I don't have any, but maybe some of you do, right? So that's something that you want less and less of. It's something called a chore. Like you don't want more of that good. So, any other examples? Yes, right. Right. So the comment is that say there's a bunch of people who are looking for a shared apartment, right? Each of them wants a room, and the apartment has say three people looking for three rooms in an apartment, and they need to divide the rent somehow. The apartment has certain rent, but you need to figure out who gets which room and who pays how much rent for that. So again, that's something you want less and less of. You want to pay as little rent as possible and still get the best room. So something like the dinner bill. Uh, yeah. So great examples. Any other thoughts? Right. Taxi fare when you're pulling the ride. Very much like the restaurant bill example. Again, you want to pay less and less of that. So great. So lots of examples. Rooms, dinner, like cake. A lot of food related examples. Uh, so these are the things you might want to divide fairly. But what's fair? What would mean what would it mean for a dinner bill split to be fair? Or what would it mean for a rent division to be fair? Right. So everyone is happy with the room that they got and the rent that they have to pay for it, for example. Right. That if everyone is happy with the deal that they got, then that's fair, right? No one is going to object to the assignment. Uh, what about cake? What what does it mean to divide a cake fairly? Cake is like, yeah, so there's this entire cake. Right, right. So okay, maybe okay. So cakes are like heterogeneous things. They might be like more chocolate on one side, more strawberry on the other side. There might be cherries somewhere, and some people like cherries, some don't. Some like strawberry, some don't. So I think the suggestion is that if you like strawberry, maybe you should get more and more of that. People who don't like strawberry, maybe they should get less and less of that. Uh, that's one way of thinking about fairness. Yes. Uh, any other thoughts? Anything else? What would fairness mean? Right, right, right. So that's like the technical term for the suggestions that we have had already. So one term that you're going to hear over and over again over the next 2 or 3 days is envy freeness. It simply means that what you have got is the best according to you. Okay, so think of the cake example. Okay, every child gets a piece of cake, right? And if it so happens that every child feels that it got the best piece according to its own preferences, so that means it does not envy any other kid, right? So that's an envy-free division of the cake, right? One can think of this notion in terms of rent division as well. So every roommate has got some room for some price, and no roommate should feel that, oh, had I got that room for that roommate's price, I would have been happier. Okay, so that's another way in which one can think about envy freeness. So we are going to see lots of fairness notions today and tomorrow, but some great thoughts out there. So let's try to sort of mathematically pin down all of these things. So here's the setup for a fair division problem. We have a set of n agents. And I'm just going to denote it by this curly n. The agents are numbered 1 to n. And we have a resource that needs to be divided. Okay, since the lecture is about cake cutting, I'm going to call the resource cake, but it's just a metaphor. You can think about any resource you like. So the reason this name cake cutting is there, why we call the resource cake, is because of two things. First is because intuitively you want more and more of the cake, right? So you don't dislike any part of the resource. The more the resource, the better. And the other thing is that cake is a divisible resource. Okay, you can cut it anywhere you like. This is in contrast to something like an indivisible resource. Say there is an inheritance that is to be divided among stakeholders, right? So there's a house, there's a car, there's a computer, there's a ring, right? Multiple people are staking their claim in it. Now you cannot divide a ring. It's an indivisible resource. It has to go entirely to one person or the other, right? So that's going to be the subject of our next lecture, the post-lunch lecture about indivisible goods. Today we are going to talk about things that can be divided infinitesimally, like a cake or like money. Okay, up to a rupee, but fine, it's still divisible, right? So the simplest model of a divisible resource is the 0-1 interval. Okay, so this is going to be our resource for today. I understand it's very boring compared to cakes and everything else, but this is the stuff that we are going to divide today. We are going to split this interval among the agents. Now, how should we do that? That depends on the preferences of the agents. And the preferences are specified in terms of what is called a valuation function. So every agent has a valuation function Vi, which simply maps some subinterval of the cake to a number. Okay, so say agent I gets this part of the resource, then its happiness or its utility for this part of the resource is, so let's say this interval is I, then its happiness is V sub I of this interval, the subinterval capital I. Okay, and this is just a number, a real number. Okay. By the way, please feel free to ask questions, or if you don't like my handwriting, please feel free to point that out. Let's keep this very informal. I don't have to like get to the end of my notes or anything like that. So, all right. So that's a valuation function. We are going to make some set of assumptions to make this object concrete, because right now it's very abstract, very arbitrary. So here are a few assumptions. On the valuation function Vi. So that's for every agent. The first is called normalization assumption. This simply means that the value of the entire cake for every agent is a fixed number, say 1. Okay. So that means for every agent I, Vi of the entire cake, 0 is this fixed number. Okay. The second assumption is what we call divisibility. So let me first write down the mathematical definition of this, and then we'll discuss what it means. So divisibility means that for any subinterval xy of the cake, uh, and any number, any fraction lambda, if you will, between 0 and 1. So the picture is that is the cake. X and y are the endpoints of some interval. This is the interval I'm talking about. And lambda is just something between 0 and 1. You choose. Okay. There should exist some z in this interval xy such that the valuation of agent I for, so I'm saying there should exist some z such that the valuation for this smaller interval is equal to lambda times the valuation for the entire interval. Okay. So in words, it simply means that every fraction of your value is also realizable by some cut in the cake. Okay. Another way to think about this is that this is like the no point masses condition. Okay. What this means is that your valuation cannot be of the form this. All of your preference cannot be concentrated at a single point. Okay, it should be spread out smoothly, continuously. Okay, and how does divisibility rule out such a thing? Anyone? Exactly, right. So all of my, so I just told you that my value, say I am agent I, my value for the entire cake is 1 unit. Okay, and this is saying that every fraction of any interval, so in particular take x and y to be 0 and 1. Yes, that means there should be some interval where for which my value is some fraction lambda. Okay, so 0.3, 0.7, 1 over pi, everything should be realizable by some interval, right? But now look at this. This is just a point mass here. So if I include this point, then the valuation for the interval will be 1 because all of my preference is concentrated at a single point, and I cannot break this point any further. You cannot break a point. Okay. So in effect, this point is like an indivisible good. You cannot break it down further. And we are going to talk a lot about indivisible goods in the next lecture. But for this lecture, this is not a valuation that we'll allow for. Okay. Question? Yeah. Yes, I'll come to that in a moment. Yeah. Yeah. Right, right. So right now the domain is just a single subinterval. I'm going to generalize valuation functions to unions of intervals in a moment. Yes. Right, right. So So I think you're thinking about, once I give you the definition of additivity of valuations, I think this point will be clear. I'll come to that in like 10 seconds. Yeah, there was another question. Yeah. No, not necessary. So this is a very, very simple model of a divisible resource, perhaps the simplest possible model. Uh, here's something you can think about, something like wackier than that. Think of a two-dimensional cake, which is how it usually is, right? You tend to have this rectangular cake. Now, so this resource will be 0, 1, cross 0, 1, right? Or n-dimensional cakes, if you're a mathematician who loves cakes. Okay. So cakes can have weird shapes, and I'm going to talk about different geometries of cakes in the open problem session. Okay. Other questions? All right. Uh, two assumptions so far. One more assumption is non-negativity, which is exactly what it says. So for every agent I, for every subinterval I, what should I write? Anybody? Yes. You don't dislike any part of the cake. That's what it means. Like nothing was burnt in the oven. So okay, here's the assumption that was pointed out in the audience. So we're also going to assume property called additivity, which means that uh, the value for a union of intervals is the sum of the value of the individual intervals. So for every I, say I1, I2, and we are only going to talk about finite unions, so no one is allowed to ask me questions about countable unions and all that jazz. Okay. No analysis for today. This is simply bi of ij. All right. Now, does that answer your question? That okay? Sorry. Yeah. So these are disjoint intervals. So the picture again is, here's interval I1, here's interval I2, on and on and on. Here's interval Ik. These are disjoint intervals. I mean, they can have overlapping boundary, like they can share a boundary, but that's it. All right. Okay, and we are also going to define something called a piece of cake. Uh, so a piece of cake is simply a finite union of disjoint intervals. Okay, so something like this is what we are going to refer to as a piece. Why am I defining this? Because when I come to the algorithms, any algorithm is going to allocate a piece of cake to any kid or any agent. Okay, so that's why it's just a good term to have in the bag. All right, so here's an exercise. Property 3 and property 4 imply a monotonicity relation. What do I mean by that? So here's an exercise for you. You have to prove this. There's another property about the valuation functions that we can infer. This means that say you have a piece S and another piece T that contains piece S. Okay. Then what should I write now? Vi of S is at most Vi of T. Larger P is the better. Okay. And try to prove it. It's very simple. Okay, so let's look at some examples of valuation functions. What is the simplest possible valuation function that fits all of these four properties? Yeah, I saw a hand going the right way, but linear. Okay, it is also linear. Um, so I suppose the simplest possible way would be like, here's your cake, here's your valuation function. Okay, I mean, you are basically indifferent. The more the cake, the longer the piece, the better. Okay, it's just like spread very evenly. Actually, what I've drawn here is something that Neil was pointing out a moment ago. These are known as a value. This is known as a value density function. So say this is your x-axis. Say the value density function is some p sub I of x for agent I. The valuation function is the integral of this. Okay, so if I'm sure everybody is familiar with cumulative distribution functions and probability density functions, think of these like that. Okay, valuation function is like a CDF. So vi for an interval is simply the integral of uh, this covers pretty much all the interesting valuation functions, and these are the ones that we are going to focus on today. All right. So whenever I draw something, keep in mind that this is not the valuation function. This is the underlying density function. But I'm going to call this valuation function anyway because why not? Alrighty. Here's another example. Something called a piecewise uniform, and it looks like, so there is some piece here for which you have this non-zero valuation. Maybe there's another piece here, and it's zero everywhere else. Okay. Now notice that the height here should be 1 for the normalization assumption. The heights here will be different because we have to respect the normalization property, right? But here's another term that you might encounter, something called a piecewise constant function. So one of the constraints in a piecewise uniform valuation is that all the heights should be the same. Okay, you can have zero and non-zero values, that's fine, but whenever you have a non-zero value, it should be the same across all the pieces. Okay, we are going to relax this constraint in piecewise constant valuation. So this creature looks like this. Maybe you have a value like this, then you have like a really high value for this, maybe like a teeny tiny value for this, and so on. Uh, suppose so. Yeah, I think so. So is the difference clear between piecewise uniform and piecewise constant? So uniform means that all the heights are uniform. Here only the heights are like some differing constants. You can call it piecewise non-uniform if you will. Okay, but again remember that the normalization property should be obeyed. So all of the areas under these towers should all sum up to 1. Okay. Here's a weirder valuation function, polynomial value density function. So I mean you can design your favorite valuation function. So maybe the valuation function looks like a polynomial, some weird. Somebody said linear, so the linear would be just growing. Okay. So these are all examples. Uh, Here's a non-example. This is not allowed. Okay. Point masses are not allowed. All right. So, question. Yeah, 100%. Need not be continuous. For example, look at yeah. I mean, yeah. So they can have like jumps, but I'm going to give you a theorem in a moment which will require continuous value density functions. So, but again, these are like the things that sort of people study a lot. These are the favorite valuation functions of cake cutting researchers. So I thought I might just put these out there. Uh, okay. Any questions so far? All right. So with all of this, now I can state what our goal is for today. Uh, our goal is to find an allocation. So I'm going to define an allocation as this tuple A1, A2 up to AN, one for every agent, of what? Of the cake. That is fair. I'm going to define what fair means in a moment. But whenever I say the word allocation, in your head you should think of each AI as being a piece of the cake, which could be a finite union of disjoint intervals. All right? And I'm not writing it down explicitly, but I'd want the entire cake to be allocated. Okay? You can't like allocate part of the cake and throw away the rest. Throwing away cake is a sin anyway. Okay? Because look, if you're allowed to throw away parts of the cake, then you might as well throw away everything, and that allocation is fair. No one gets anything, right? So we are not going to deal with such bad allocations. Okay. So here's again the picture. Here's the cake. Say agent 1 gets this. Uh, Maybe agent 2 gets this part, and maybe some agent 3 gets the rest of the cake. All right? That's the object that we are going to be working with today. Okay. Question. Yes. Is the integral so far here? So you start from here, and you look at the area under the curve basically. Yeah. So this is the probability density. Valuation function is the integral. So uh, right. So for example, it might be validated for. So let's integrate this curve. Okay. So far the area is 0, and boom, it shoots up to 1. So there's a discontinuous jump. Right. Uh, right. Divisibility implies no discontinuity. So okay, I suppose you can work with like a finite number of discontinuities, because these things, most of the results that I will tell you about go through for Lebesgue integrable functions. So like a finite number of discontinuities are okay, but I just didn't want to get into all of that. I just want like very plain and simple. Maybe think about it. Yeah, maybe we can talk about it after the lecture. But that makes sense. So I should write like 1 over n times the value for the entire cake, but because of the normalization property, it's just 1, so I just ignore it. Okay. So say there are 3 people, then a proportional allocation gives every agent 1/3 of its own preference, of its own valuation. The next property was already hinted at by someone. It's called NV freeness. So the way you define is that for every pair of agents, no agent should envy any other agent. So let's look at agent I, and agent I is comparing its own allocation AI and somebody else's allocation AJ. Okay. Envy freeness requires that Vi of AI, meaning I's happiness for its own piece, should be at least as much as I's happiness for the piece of any other agent. And this should hold for every pair of agents. Questions? All right. Okay, so I have a question for you. Is one of these properties stronger than the other, or are they incomparable? So suppose an allocation is proportional, is it also NV free? Or if an allocation is NV free, is it also proportional, or none of these implications hold? NV free implies proportional. Why?
For all I mean, it should sum up to 1. So
Yes.
take that, then it has to be greater than 1.
Right, right. So does everyone get that? So think of it. Think of an allocation A1, A2 up to AN. Say I say it is NV free. Okay. So agent I thinks that its piece is better than any agent J's piece. Okay. Now we know that for any agent, all of these pieces should sum up to 1. So Vi of A1 plus A2 plus A is equal to 1. And one of the pieces Vi of AI is any other piece, which means what? Which means that Vi of AI should be at least 1 over n, right? Because if the biggest piece is smaller than 1 over n, they won't sum up to 1, according to I's assessment. Yes? Right, but does it hold for every ij? Okay, so far we know this. I'm going to use EF for NV free and prop for proportionality. So far this holds. But think about it, proportionality need not imply NV freeness, right? So say there are 3 agents, okay? Say I'm one of the agents and I got 33%, 1/3 of my own value. But there might be someone else out there who's getting, say, 50% of my value. So although my proportionality is satisfied, I'm getting 1/3 of the entire cake. There might be someone else who, according to me, is getting more than 1/3. Yes? Everyone buys that? Okay, so proportionality need not be true, need not imply NV freeness in general. But what if there are only 2 agents? You and a friend of yours. Yes, to what? Why? Right. Right. Yeah. Right. Yeah. So someone answered that for 2 agents, when n is equal to 2, proportionality actually, the implication holds in the reverse direction, that proportionality implies NV freeness. The reason is very simple. Uh, for a proportional allocation with 2 agents, every agent should feel that it is getting at least half of the cake according to its own assessment, right? So if you're getting at least half, the other agent is getting at most half. So you don't envy that agent, right? Okay. So EF implies prop, and prop implies EF only for n equals to 2. So these two properties become the same when you have only two agents. Alrighty. So now that we know what fairness means, let's get into the questions. So we are going to talk about two kinds of questions. The first is going to relate to existence of fair allocations. So suppose I give you a cake, 0, 1 interval, I give you n agents, and I give you the preference functions, the valuation functions, v1 up to vn, and I ask you the question, does there exist a fair allocation? Meaning, does there exist an envy-free allocation, or does there exist a proportional allocation? Yes or no? Okay, it's a pure existence question. And if such an allocation exists, can you design algorithms for computing such allocations? Okay, that's the computation question. All right, so turns out that there's a very clean answer to question number 1. It's a very nice theorem by Nogalan. Here's the theorem. So say v1, v2 up to vn are valuation functions that are induced by continuous value density functions. For example, the polynomial or the uniform, these things are valid. Value density functions. Then it is possible to cut the cake at n squared minus n places. Simply means that at the 0, 1 interval I make n squared minus n marks on the cake, which means I'm left with n squared minus n plus 1 many pieces, many disjoint intervals. And reassemble them, reassemble the n squared minus n plus 1 things into an allocation a1 up to an, such that, and this is where the result really hits you. So vi of aj is equal to 1 over n. So here's what the result is saying. You are given these valuation functions which are induced by continuous value density functions. So still a fairly broad class, maybe not all encompassing, but whatever. Then it is possible to cut the cake. Here's the cake. I'm going to take a knife and chop it up at most n squared minus n places. So I'm left with n squared minus n plus 1 distinct pieces. I can reassemble those pieces into n piles or n bundles. So I get an allocation a1 up to an, and that allocation has this magical property that every agent I values not only its own bundle at 1 over n, it values every other bundle at 1 over n as well. Okay, so this is weird. I mean, this should not happen. Is the theorem statement clear to everybody? So in particular, let's ask the question. So we have learned two fairness notions. Is such an allocation fair? Is it proportional? Yes? Anyone who thinks it is not proportional? Okay, why? Because every agent is getting 1 over n. Is it NV free? Yes, how many yeses? Okay, pretty much everybody. Okay, why is it NV free? Everything is 1 over n, so you don't have any extra preference for any other piece. So this is a very unique sort of partition of the cake. There's a word for it. It's called the perfect partition. This is like the ultimate way of having a fair allocation. Okay, so that's great. This is a very general existence result. NV free allocations and proportional allocations exist in a very broad sense. But the downside of this result is that it is a non-constructive result, meaning the proof of this theorem does not come with an algorithm for constructing such a perfect partition. Okay? So that's what we are after now. We want to actually find fair partitions. So how do we do that? Question? Okay. So note that valuation functions are these continuous objects, right? They can have weird shapes. They are defined over 0, 1. Whereas algorithms are, the way we think about them, are discrete objects that define in a step-by-step manner. So we need to define a way in which a discrete object, i.e. an algorithm, interacts with a continuous object, i.e. a valuation function. Okay, we need to formalize that before we actually start coming up with algorithms. So there's a very nice model for formalizing the way in which an algorithm can interact with the valuation function. This is called the Robertson-Webb query model. So the way we are going to think about algorithms is that each algorithm issues a query to a valuation function. I'm going to define what those queries are in a moment. So algorithm asks a question about the valuation function, and some oracle gives the answer to that question. Okay? And the complexity of an algorithm will be measured in terms of how many questions are asked by the algorithm in order to arrive at a fair division. All right? So let's question. I'm not going to prove this, sorry. The proof, I mean, yeah, you're welcome to look at Alon's paper, and it's in the references on the web page. Yeah, it is a non-constructive proof, and it uses some pretty heavy machinery. So so okay, here's an exercise for you. Okay, so if you want to compute NV-free allocations, so note that these kind of valuations do not satisfy the hypothesis of the theorem because these are not induced by continuous value density functions. But try to think about, so if the preferences of agents are given by these kind of piecewise uniform or piecewise constant valuations, try to think about algorithms that give NV-free, that construct NV-free divisions. Okay, so once I give you the query model, which I'll do in a moment, I promise, try and think how which algorithm is going to which algorithm works for these kind of valuations. So say every agent's preference is given by a constant number of such buildings, okay, such towers. Okay, I'll give you a hint. Look at these breakpoints here. Okay, say you know what these breakpoints are. All right, so every agent has these weird valuations, and you have these breakpoints. Now, as an algorithm designer, your task is highly simplified if you go from one breakpoint to the other. Look at the intervals between consecutive breakpoints. Okay, those maybe some agents value those intervals, others don't. Right, and you need to think about how to divide each consecutive interval how to give out the peace between between consecutive breakpoints to the agents such that you have an envy-free division. I won't say anything more than that, but if you are not able to, if you have any questions about this, come and talk to me. Okay. But this is a nice exercise. This does not require any of the heavy machinery there. There are much simpler algorithms for these kind of valuations. Yes, yes, and we are going to see that today. I'll give you the algorithm exactly. Two players is like very neat and very nice. Okay, so now I'm getting into the second part, which is the computational part, and I need to define a query model. I'm going to define the Robertson Web query model. And there are two kinds of queries here. One is called a cut query. The other is called an evaluate or eval query. So in the cut query, the algorithm asks agent I the following question. Say there is a point X on the cake. The algorithm asks player I, hey player I, starting from point X, make a mark on this cake such that your valuation for that the enclosed bit is alpha. Okay. So when player I is asked this question, it returns, so or player I or agent I returns a point Y such that Vi of xy is alpha. So the algorithm is requesting a cut point here. Okay. This is one way to ask about the valuation function. No, get some information about the valuation functions, right? The other query is the evaluate query, and it is even simpler. So again, the algorithm asks player I, hey player I, here are two cut points. So here's the cake again, here's X, here's Y. Tell me how much you value this piece. Okay? So player I says my value is this. Everybody happy? All right. So there's a subtlety that I want you to keep in mind about these things. Note that, for example, in the cut query, the number Y is not required to be a rational number. Okay? It could be an irrational number. And that's okay, because the kind of computational model that we are going to talk about today is a query model. It's not a Turing computation model. There's no Turing machine involved anywhere. The complexity of an algorithm is measured by how many such queries it has to ask about the valuation before it arrives at an allocation. Okay. The algorithm you can think of as having infinite computational power. That's okay. The hardness of the problem is measured in terms of how much information about the valuations is needed to come up with a fair division. Okay, that's the notion of hardness. It is not polynomial time or NP hardness or any of those things. Okay. Okay. Let me just write that the complexity, put it in quotes, is the number of Robertson web queries, RW queries, or simply queries. Great. Now let's get into the real deal. Cake cutting algorithms. Now I'll start with the simplest case where we only have two agents. N equals to 2. And I'm sure most people know this algorithm already. It's called the I cut you choose algorithm. So just going by the name, can anyone guess what the algorithm is? Yeah, a little more elaborate. Yes. Perfect. So that's exactly correct. Uh, First, let me write down the English pseudocode of this algorithm. Then we'll write how we can, how we can rewrite this algorithm in terms of these queries. Okay. So, like somebody said, say agent one makes a cut in the cake such that the two pieces are equal in its assessment. Okay. So agent one cuts the cake into two equal pieces, right? And then the other agent has a choice. Okay, it can pick any of the pieces, and any rational agent is going to pick the piece that it likes better. All right, that's the algorithm. How do we write this English pseudocode in terms of these Robertson web queries? Yeah. It could be. It could be. Yeah. So I haven't given the queries yet. Let me write the queries first. Uh, so anybody, how do, yeah, question. Yeah, sure. Go ahead. Cut one of 0 comma half. Is that correct? What does cut one of 0 comma half do? Exactly. So player one, starting from the 0 endpoint, it gives you a y such that its value for the piece 0y, and therefore for the piece y1 is both they are both valued at half. So that's exactly right. What about, you want to take a guess at the second one? Yeah. So say this was a cut point y. Okay. Now the suggestion is to evaluate for the second player. Okay. 0y. Okay. I mean, one evaluate query is sufficient because of normalization, right? So if this thing is bigger than half, you assign this piece to player 2. If not, you assign the other piece. Two queries. That's it, right? Okay. What can we say? Yeah, question. Fantastic. Yes, that's true. Well, so that cannot happen because think of a situation where both agents have this uniform valuation. No matter where you cut, the valuations are going to sum up to 1. So if one agent gets bigger than half, the other has to get less than half. You can't get past this. Okay. So the question was, the first agent is making a cut, right? And it's making a cut at half. So there's no way it can get more than half. Second player can get more than half, right? And the question was, well, can both players get more than half, right? There seems to be an asymmetry, but not under this algorithm. It's not guaranteed. One down ensures two queries, you get NV free allocation for two players, and therefore also a proportional allocation, right? So we have our first theorem. For n equals to 2 and n be free and therefore a proportional allocation, can be computed always with only 2 Robertson web queries. Okay, so this is also a proportional allocation. That's great. That's a good start. Let's think more about proportionality for a second. Okay, so we know how to compute proportional allocations for 2 agents. What about more agents? 3, 4, 5. Any ideas?
First agent asks for a cut which returns. So it will ask 0, 1 by cut to it, and on the so agent will ask similar cut 0, 1 by on the remaining case.
Fantastic. So that's a very, very nice suggestion, and that's exactly the algorithm I had in mind. So it turns out that you can compute proportional allocations with n agents, okay, and the algorithm is called the Dubin-Spanier. I think this algorithm was actually by Banach and Canaster, but I'm following the cake cutting chapter. So in there it is called Dubin and Spanier. Someone should check this. But whatever, what's in a name? Okay, so let me describe the informal version of the algorithm, and then we'll write the query based form. So the suggestion is, say you have a cake 0 to 1. Okay, think of a moving knife that is moving from 0 towards 1. Okay, now as I'm moving the knife from 0, I ask, say you guys are the n agents. As soon as somebody's valuation for the piece on the left reaches 1 over n, they should shout stop. Okay, as soon as anybody shouts stop, I'll make a cut and I'll give that piece to that agent and kick out that agent. All right. So what do I know about that agent? Does it get its proportionality? It does. What do I know about the other agents? Sorry, I heard something. Sorry, can you say it again? Haven't got it up till now, but what's there in the rest of the cake for them? How much do they value the rest of the cake? More than how much? N minus 1 by n, right? Okay. So the remaining cake has value at least n minus 1 by n for each of the n minus 1 agents. Okay. So let's think of this as our new problem, right? So n minus 1 is like the new n, if you will, and the remaining cake is the new cake, right? If I now do the same exercise, I slide the knife from left to right, and I stop as soon as somebody's proportionality is reached. Proportionality in this case is 1 over n minus 1 times the value for the entire cake, which is at least n minus 1 over n. Then once again, I can kick out an agent with its proportionality score with respect to the original cake. Everybody with me? So here's the picture. Slide your knife from here. As soon as some agent shouts stop, throw away this part, allocate it to say agent 1. Rest of the cake is at least n minus 1 over n for every agent. So the corresponding proportionality threshold is this, which is, well, this thing is 1 over n. So at least 1 over n mass is left in the cake for every agent. So I can just keep repeating this and I get a proportional division of the cake, right? Now the last agent is going to get at least 1 over n, whereas everyone before that agent gets exactly 1 over n. Everybody happy? Okay. Can someone quickly suggest how many queries I need for this? Cut and eval queries. Yeah, so that's correct. Anyone else? Any other answers? Okay. Oh, by the way, do people want me to write this algorithm down, or is it okay if I skip it? Should I skip it? Everyone understands the algorithm? Okay, so exercise, write the algorithm in terms of the Robertson Web language. Okay. And someone should tell me how many queries are required. But I'll just give you the theorem that for any n, a proportional allocation can be computed with as of now unknown number of queries. Okay, someone should tell me how many queries there are. Questions? All right. So let's get into the final algorithm of the day, which is about NV freeness. So now that we know everything about proportionality, let's move to a stronger notion. So someone to think about NV freeness for, so we know how to compute NV free for 2 agents. What about 3 agents? Here are the definitions. Take a quick look before I erase them. The algorithm turns out is quite clever and quite non-trivial actually. At least if you're thinking about it for the first time. Uh, so it's called the Selfridge Conway algorithm. So now I'm thinking about NV freeness for n equals to 3. Okay. So we're only focusing on 3 agents and we want NV freeness. Let's give the agents some names, which would be helpful. So say the agents are A, B, and C, and the cake is, well, the cake. Uh, this algorithm works in 2 phases. Phase 1 starts with something that looks very much like cut and choose. I mean, at least the cut part. So agent A divides the cake into 3 equal pieces, equal according to its valuation. So say this is the cake. Agent 1 comes and says, okay, here and here. So there are 3 parts. Each of them is worth 1/3 to me. All right. Now agent B comes into the picture. And he looks at all these 3 pieces. Okay. If there is a favorite piece for agent B, meaning if one piece is strictly better than the other 2, then the algorithm asks agent B to create a 2-way tie for the largest piece. Okay. How does it do that? Well, say agent B thinks that this is like a really, really good piece. This is the best. say this is the second best. Basically, let's say agent B looks at them in terms of their lengths, okay, for simplicity. What it is going to do is it's going to trim the piece such that the value of the remaining piece, let's set aside this stuff, the value of the remaining piece matches the second best. Okay, so there's a two-way tie for the largest, the best piece, according to agent B. Everybody with me so far? Okay, so I'm going to call this thing the trimmed piece, and the leftover stuff I'm going to call them the trimmings or the crumbs, whatever. Okay, the one point is here. So that's the main cake on top and the leftover at the bottom. All right. Now agent C comes into the picture, and now basically the algorithm allows the agents to each pick a piece from the main cake. Okay, so agents C, then B, then A, pick a piece each in that order. So this is the agent who hasn't had a say so far. This gets to pick a piece first, then the agent that created a two-way tie, and then the cutter from the step one. All right. Each of them gets to pick a piece from this part of the cake. We are not touching that part. Okay. But there's a condition that if the agent C, the first one to pick, did not pick this piece, the trimmed piece, then agent B has to pick that. Okay. So the condition is that agent B picks the trimmed piece if agent C does not. All right. In particular, that means that agent A never picks the trimmed piece. Okay. So far we have a partial allocation of the cake. Okay. So there's some part still left over. We'll get to that in a moment. But what do we know about the allocation so far from phase one? It's NV free. Why? C does not envy anybody because he gets to pick the first, right? So it has a choice of picking its favorite piece, so that's fine. B created a two-way tie, right? So if it does not get one of the favorite pieces, it gets the other. Either way, it's getting its favorite piece from this part of the cake. Yes. So if you focus only on this part of the cake, B is not envying agent C. Yes. And what about A? A was the one who cut the cake into three parts. So yeah, the last only way NV could have been generated is had A got this piece, but we explicitly ruled that out. We said that A is not getting this piece, right? A never gets the trimmed piece. Everybody with me so far? It's important that we understand this bit before moving on. Okay. Okay, let's move to phase two then. What can we do now? We know how to create an NV-free partial allocation of the cake, right? We just discussed that. So what do we do with the trimmings? Can we rerun phase one? We can. what happens then? If you read in phase 1, maybe you get another round of trimmings. If you read in phase 1 on that, maybe you get another round of trimmings. You'll never finish, right? So you can't just like blindly recurse that way. You have to do something more subtle. Ideas? What is one thing that we know about the trimmings? So let's treat the trimmings as a cake, as a full-fledged cake now. What is one thing that we know about the trimmings that we did not about the original cake? There's something we know about the trimmings, right? Exactly, yeah. So for example, we know that, okay, let's say in this phase, agent A picked this piece, C picked this, and B picked this, say, okay. Even if the entire trimmings go to B, A could not care less. Yes? Alright. What does that tell you? So suppose I do this cut and choose business for 3 players on this new cake, the trimmings. A can come later in the order than this guy, whoever it is, B or C. Because it's not going to envy even if the owner of this piece gets the entire trimmings, right? So when we suppose we do this cut and choose business and we have this order of agents, right? C then B then A. I can happily place A later in the order after whoever got this piece, B or C. And that's not going to disturb envy in any manner, right? When we started out this algorithm, we did not have that luxury. We did not know what the order should be, but now we do. There's this extra nugget of information that we have, and you'll see that this helps. So so let's go with this. So say B got the trimmed piece. You can rewrite this in terms of C getting the trimmed piece. I'm not going to do that. Say B got the trimmed piece. Look at the agents that got the untrimmed piece out of B or C. That is our new cutter. Okay. So C is going to cut the trimmings into 3 equal pieces. And I'll put this in quotes because it's not specifically agent C, it's the agent that gets the untrimmed piece. Sorry, say it again. Why do you have to? So what's the suggestion? Well, so here's the little thing, right? So suppose, I mean, maybe I can do a cut and choose between B and C here, but then C might get this and some part of this. So it's getting 1/3 plus blah, and A might start envying C, right? So right now C is getting exactly 1/3 according to A, but if I do not involve A here, it might get something else. So that might generate envy. More questions? A little louder. Yes. Yes. Okay. Oh. So I didn't. A doesn't care if the owner of the trimmed piece gets the entire trimmings, but it does care if any of this stuff goes to the owner of this piece. Yeah, okay, yeah, that's another subtlety. So C's favorite piece for this main cake was this one, but maybe for the entire cake, this may no longer be the favorite piece. That's another thing we need to keep in mind. Good point. Yes. More questions? Please ask questions because it's a very sort of a delicate argument. So Everyone is looking forward to lunch. Okay. Okay. So let's. Yeah. At this point, we only have a, an NV-free allocation of a partial cake. That's all I have right now. Yes. Uh, what I'm going to do. So here's the spoiler. I'm going to create an NV-free allocation over the trimmings as well. Okay. I'll show you how to do it in a moment. Now I have one partial NV-free allocation. I have another partial NV-free allocation, and these are completely disjoint. What if I take the unions? Is it still NV free? How many people think yes? How many people think no? I mean, not necessarily. Some people think not necessarily. Okay, so let's do this exercise. Say you have an allocation A and allocation B of disjoint entities. Say this is NV free. Agent I is getting something here, something here. So Vi of AI is at least Vi of AJ. NV freeness for the top cake. NV freeness for the bottom cake. Additivity. Okay, so if you combine two partial allocations of disjoint creatures, you still have NV free. That preserves NV freeness. Okay, so that's why we can go ahead with the rest of the algorithm, and it's very simple. It's only 2 steps. Phase 1 was 3 steps. So the cutter, whoever gets the untrimmed piece, cuts the cake into 3 pieces, 3 equal pieces according to its assessment. It's equal. All right. Now I'm going to again do this order thing. I'm going to make the agents pick the pieces in an order. What should be the order? Someone to shout out. Sorry, loudly. I heard some. BCA. BCA. So note that if C picks before A, then A might and be C. So we can't let C pick before A, and there's a reason why C is the cutter. C divided everything into 1/3, so we can happily place C at the last position and be assured that it's getting 1/3 of that 1/3 of the cake. So C is surely going at the last. Who's the first and who's the second? I just told you earlier that A should go after whoever got the trimmed piece, right? So here's the order: B, then A, then C, in that order. Pick a piece each. Yes? Okay. Just to be sure we are on the same page, is this allocation of the trimmings NV free? Just the partial allocation. Well, C does not envy anybody because it's the cutter. A could have envied B, but it does not because of this irrevocable advantage that it had. Yes? And B is the first one, so it does not envy anybody. We have 2 happy partial allocations. Combine them and you can go home. Sorry? C is like a placeholder. So if the phase 1 allocation looked like this, then it would be agent B, and it would be the cutter, and C would be the first one to pick. They exchange their roles. Yeah, sorry, this is the trimmings. Sorry about that. Does everybody believe that we have an NV-free allocation for 3 agents? Sure, question? Yeah, let's go over that again. So say after phase 1, this was the allocation. Okay? So C got the trimmed piece. Now think from A's viewpoint. Even if C gets the entire of the trimmings, it's not going to envy C, right? So when we play this 3% cut and choose on the trimmings, A can go after C, right? So we have sort of fixed that part of the order. That luxury we did not have earlier because we did not know anything about the original cake, but now we know that about the trimmings. So there's this notion of irrevocable advantage that A has over the person who gets a trimmed piece, and that makes this possible. Otherwise we would have run into the recursion and it would have never stopped, right? Okay, so theorem for n equals to 3 and EF allocation can be computed with using, again, unknown number of queries. Someone should tell me how many. I promise a cold coffee for the correct answer. Okay? Alright. Do we have any time left? How many? Do I have like 5 minutes? Okay. So there's a couple of like nuggets I want to just share. We're done with the theorems and algorithms. Turns out that the game for n bigger than 3 is very interesting. So there is a protocol that finds an envy-free allocation for any n. Okay. The trouble is that it is an unbounded protocol. So no matter what valuations you give me, the protocol is guaranteed to terminate, so it's finite, but there is no bound that you can give that it will terminate after so and so steps. Okay. In other words, its running time depends on how complicated the valuations are. You can always cook up weird preferences and make that protocol run for as long as you want. But it terminates. We just don't know when. Okay, so it's by Grams and Taylor. They have a finite but unbounded EF protocol or algorithm, if you will. Okay, so not very useful because we don't even know like how long it will take. So this was a big open question, that does there exist a bounded envy-free protocol for general n? Okay, and so far it should be open for all of us. I haven't given you the result, but okay, do people understand the difference between finite and bounded? Finite means it will terminate. Bounded means that its termination time is some function of n, not a function of the valuations. Okay, if it depends on valuations, you can cook up some strange preferences and make it run for, make the bound very loose. But here's the very interesting development. So yeah, so it means that you give me an integer, I can cook up valuations that make that algorithm run for that many steps. It cannot. So it cannot only depend on n, because once you fix n, then I have a bound. I'm saying fix an n, say n equals to 4, but the preferences can be very, very complicated, and the algorithm's runtime depends on that, even with constant number of agents. So I think for 5 or 6, it's like that. So this was like recently there was this like big breakthrough in the world of fair division. By these two researchers, and this is all very, very recent stuff, last couple of years. They showed that there does exist a bounded envy-free division protocol. Okay, so the running time bound, or the query bound specifically, depends only on n and not the valuation functions. Once you fix the number of players, you know that okay, the algorithm will terminate after these many steps, no questions asked. Okay, but there's a slight glitch, and the glitch is that the bound is sort of big. It's actually quite big. It is this. So yeah, it is. It's bounded. It's a function of n. Once you fix n, you know that the algorithm will terminate in that many steps. But I dare you count that even for n equals to 2. No, no, no. It's 6. It's a universal constant 6. Great question, and thank God it's not. It is like a constant number of ends in the tower. Um, so it is what it is, and it is one of the big open questions right now to figure out what's the right bound. So this is the upper bound, like order. Don't even have that big an O. That there's also a lower bound, which says that any envy-free algorithm on some bad input will require at least these many steps, and that number is n squared. So there's a bit of a gap. um, and people are welcome to think about better protocols.